Welcome back to another explainer. Okay, today we are looking at something, well, honestly, it's completely mind-bending in the world of software preservation. I mean, imagine an AI that isn't just generating code, but actually building a complete custom reverse engineering laboratory for another AI use. We're talking about setting up a highly controlled digital sandbox designed specifically to dismantle, analyze, and then perfectly rebuild legacy 1992 DOS software, like the classic game Overkill. So this isn't your standard AI code generation. This is literally an AI constructing the exact tools it needs to reverse engineer software entirely on its own. So let's take a quick look at our blueprint for today. We're going to start with how the AI builds its lab, then we'll move into the strict rules of the Oracle, explore the proof engine, walk through the automated lifting loop, and finally, we'll see how this AI graduates its creation into a standalone modern port. All right, let's get into it. Starting off with Section 1, AI building an AI lab. Basically, setting up the ultimate autonomous environment. Now, if you've ever poked around a legacy DOS codebase, you know it is, well, it's a beautiful, tangled mess. Developers back then were using literally every trick in the book just to squeeze performance out of super limited hardware, which resulted in this tangled, incredibly hardware-specific machine code. And that's exactly why the source material explicitly states this is a framework built by AI for AI. See, this project isn't about an AI hallucinating a modern remake just by looking at a couple of screenshots. No way. Instead, an AI agent is handed a manual and the original game files, and it's tasked with building its own specialized tracing and analysis tools. It has to figure out the rest and construct a flawless, native source port from the inside out. And because this environment is so insanely controlled, the recovery process is entirely evidence-driven. The AI doesn't guess at all. It doesn't rely on generic patterns of, how DOS games usually work, because let's be real, in 1992, developers were using every duct tape trick imaginable just to save a few kilobytes of memory. So instead, the AI uses this custom laboratory to trace exactly what the original executable did, literally CPU cycle by CPU cycle. This guarantees that the final rebuilt product crystallizes solely from hard, verified evidence. What's really funny here is just looking at the sheer imbalance of labor on this setup. The human's job, it's basically just providing the legally owned game files, maybe playing a quick round to record an input demo, and then just sitting back to playtest. That's it. Meanwhile, the AI agent is handling literally all the heavy lifting. It's booting the virtual machine, probing the memory, finding boundaries, recording regression proofs, recovering routines, and fixing any byte-level divergence. It's basically the ultimate digital lab assistant. Moving on to Section 2, the sandbox and the Oracle, establishing the unshakable source of truth. So to reverse engineer something this delicate safely, the AI actually had to build a custom 8086 interpreter and DOS/BIOS service environment. And this really perfectly illustrates the difference between its lab and what we're typically used to. I mean, we all know DOSBox, right? It's built for playing games. It favors speed and user experience. But this custom deuce_re framework VM, it's a bespoke workbench built entirely for observation and reverse engineering. It favors strict determinism and byte-exact state verification. Think of it as a highly sensitive scientific instrument designed specifically for data extraction, not just a toy for entertainment. Sitting right inside this custom VM is what the project calls the Oracle. The Oracle is the original 16-bit DOS binary, and it functions as the unquestionable single source of truth. This is actually the core philosophical rule of the entire project. When the AI writes a clean, native routine to replace some old code, that new code is merely a hypothesis. And it remains just a hypothesis until it perfectly matches the exact behavior of the Oracle. That brings us to Section 3, the deterministic proof engine, measuring hypotheses against observable reality. So you might be wondering, how exactly does the AI prove its hypothesis actually matches the Oracle without any human subjectivity? Well, it relies entirely on rigid math. It uses full machine snapshots and deterministic demo recording and replay, which ensures the exact same keystrokes happen at the exact same microsecond every single time. Then it uses differential per hook verification and lockstep frame-by-frame comparison just to rigorously check its work. The takeaway here is that every single finding is replayable and every claim of equivalence is mathematically checkable. The strictness here is just absolute.
A hypothesis is only accepted if it perfectly matches the oracle's original assembly state, across the board. We're talking CPU registers, system flags, full memory layout, the stack, and even file ports. And this level of, well, paranoia is completely necessary to handle notoriously difficult problems like self-modifying code, where the game is literally rewriting its own instructions on the fly. There are no silent fallbacks here. If an AI-recovered path fails this byte-for-byte check, it fails loud. The program halts, throws an error, and that failure simply becomes the AI's next task to solve in the lab.
All right, on to Section 4, the automated lifting loop, replacing the game piece by piece. Now, this loop is essentially the practical scientific method the agent uses to actually dismantle these legacy titles. It acts as an automatic code lifter, autonomously swapping out ancient machine code for modern Python. Here's how it works. Step 1, the AI runs the original executable inside its controlled VM. Step 2, it targets and hooks individual hot routines right at their original memory addresses. Step 3, it lifts and rewrites that specific routine into high-level readable Python. And finally, Step 4, it runs both the old ASM and the new Python simultaneously and compares the state, byte for byte. It just loops this process, safely transforming the game piece by piece. There's actually a really fascinating development rule that governs this whole loop. Fidelity first, readability second, meaning third. Basically, the AI is explicitly instructed not to get creative. It never invents gameplay names, object classes, or mechanics without rock-solid evidence backing it up first. Like, it doesn't just name a memory address player health because it kind of looks like it. No, it waits until the mathematical evidence undeniably proves that's what the data actually represents. The AI follows what's called a semantic crystallization plan. It starts really small with isolated leaf routines, things like graphic splitters or asset decoders. Then, once those are verified, it moves deeper into the actual gameplay logic. Slowly but surely, it promotes these stable hooks upward, stripping away dependencies on ancient CPU registers or segment offsets. It's essentially morphing the game from an opaque black box of machine code into a beautifully structured native architecture. And finally, Section 5, retiring the virtual machine, graduating into a pure native source port. This right here is the end game of the AI's laboratory work. Right before graduation, the AI uses a state mirror bridge. And honestly, this is the ultimate technical flex of the project. At this stage, you've got clean, readable native code running the game on top, but underneath, this bridge maintains exact mathematical equivalence with the old chaotic DOS memory layout. It ensures that even as the code becomes entirely modern, its soul, its mathematical behavior is still perfectly verifiable against the oracle. Once that final verification is done, the transformation is completely finished. The game no longer needs the emulator hot path to run at all. It boots natively, cleanly, right from the original data files. At this point, the AI actually decommissions its custom virtual machine laboratory, moving it to the Oracle seat, basically keeping it around purely for offline testing, demo replays, and debugging. The lab has successfully birthed a perfect modern clone. And get this exact same process is now even being attempted on 16-bit Windows games through a spin-off framework called Win16_Re. How cool is that? Which leaves us with an incredible realization. Think about it. If an autonomous AI agent can build its own deterministic laboratory, set up strict mathematical proofs, and perfectly reverse engineer a chaotic 1992 DOS game completely without human intervention, what other legacy black box systems is it going to dismantle and seamlessly rebuild next? The implications for software preservation and modernization are absolutely staggering. Thank you so much for joining me on this explainer. I hope you found this AI engineering as fascinating as I did.